This next lesson involves a system where we can use trigonometry, which comes out of triangles that have acute angles, and be able to apply it to angles that are greater than 90. In fact, we can do angles anywhere between 0 and 360, and then actually beyond that. What we're going to do is start with understanding how this system works. In order to do that, I'm going to have you use skills that you already have in terms of labeling right triangles and identifying what the trig ratios are. And so I'm going to have you start learning how this system works by going through and labeling the triangles in each of these 4 Cartesian planes that are here. First of all, just to talk about the system for a moment, it uses the Cartesian plane, and it's for angles between 0 and 360, and as I said, beyond that. In order to be able to associate trig ratios with angles outside of 0 degrees to 90, we put them on a Cartesian plane. A right angle triangle is placed in each of the quadrants. What happens is you have 4 identical triangles in all 4 quadrants. Each of these triangles are labeled by opposite, adjacent, and hypotenuse, just like we typically do. The key, however, is the fact that when we put this triangle, and I'm working with the 30-degree triangle in this example, when we put it in the next quadrant, this acute triangle here is now being associated with its supplementary angle, which is 150 degrees. All of these angles in this system are measured from the positive x-axis. So you can see the arrows start on the x-axis and go to the terminal arm, or it's also called the radial arm, which represents the end of the angle where it terminates. So essentially what happens is that an acute triangle is used to represent the ratios for a triangle that is. What happens is that an acute triangle is used to represent the ratios for an angle that's larger than 90. So you can see here in this 30-degree triangle, if we were to draw the vertical axis, we would have all the same numbers on the sides as this triangle in the first quadrant. The only difference is that some of these sides would have different signs. For example, in this triangle, this side, which is the negative x-axis, will be negative. That's what's going to distinguish these sets of ratios from this set, and similarly the other sets. As a result, we then can use in construction or in other applications, machinery, etc., we can use the idea of having an angle that's greater than 90 and still work with trig ratios. So to get you to become familiar with this system, what I would like you to do is write all of the primary trig ratios for each of these triangles. So in the first one, you would write sine of 30 and then equals the values. And notice that this angle that I've chosen is a special angle. So you're going to label the sides with their exact values. This one is the 1, 2, 3, which is actually 1, 2, and root 3. And then write the 3 ratios. Now, when you come over to this angle here, instead of writing the sine of 30, you will be instead of writing the sine of 30, you will be writing the sine of 150, because this triangle here is the triangle for the angle 150 degrees. The same will happen down here, the sine of 210, and then the cos of 210, etc., and the sine of 330, the cos of 330, the tan of 330, all taken from the acute triangle where this angle is called the related acute angle, and it's the reference point for the opposite, the adjacent, and the hypotenuse. So go ahead and give that a try, and then you can watch as I do it to check your answers. Starting with this first triangle, this is the 1, 2, root 3. All of these sides are positive. This is what we're used to starting in grade 10 with trigonometry. The sine of 30 is equal to the opposite over the hypotenuse, which is 1 over 2. The cos of 30 is equal to the adjacent over the hypotenuse, which is root 3 over 2. The tan of 30 is equal to the opposite over the adjacent, which is 1 over root 3. If we were to rationalize this, this would be root 3 over 3 because we would multiply the numerator and the denominator both by the root of 3. Now, coming over to this triangle, we form a right angle triangle. Remember that the convention is, in this system, you always drop a perpendicular line from the end point of the terminal arm to the x-axis. Now what we're doing is the sine, cos, and tan of 150 degrees. This is also the 1, 2, 3, 1, 2, root 3, but this side is minus. The sine of 150 degrees is equal to the opposite over the hypotenuse, which is 1/2. The cos of 150 degrees is equal to the adjacent, which in this case is minus root 3 over the hypotenuse, which is 2. This is minus root 3 over 2. The tan of 150 degrees is equal to the opposite over the adjacent, which is 1 over negative root 3. So we have negative 1 over root 3. Once again, if we want to rationalize this, we would end up with negative root 3 over 3. Coming down to these triangles, negative 1, 2, and negative the root of 3. The sine of 210 degrees is equal to the opposite minus 1 over the hypotenuse, which is 2. That's minus 1/2. The cos of 210 degrees is equal to the adjacent over the hypotenuse, which is negative root 3 over 2, giving us negative root 3 over 2. The tan of 210 degrees is equal to the opposite over the adjacent, which is negative 1 over negative root 3, which works out to same sign positive. So we have positive root 3. Coming over to this fourth triangle, negative 1, 2, and remember the hypotenuse or the terminal arm is always a positive value. And we have a positive root 3 here. The sine of 330 degrees is equal to the opposite minus 1 over the hypotenuse, which is 2. We have minus 1/2. the cos of 330 degrees is equal to the adjacent, which is root 3, over the hypotenuse, root 3 over 2. The tan of 330 degrees is equal to the opposite over the adjacent, that's negative 1 over root 3. Rationalizing that, we end up with negative root 3 over 3. Now, a few things to stop and make note of in this system. Notice that for any acute angle, there are 4 other positions for that angle to be drawn to form an acute triangle that relates to obtuse or oblique angles. So in all of these cases, the values of the angles in terms of their magnitude are the same for each of the 3 ratios. What distinguishes this set of ratios from this set and so on is the fact that there are negatives in the other sets. So this set right here are the ratios for 330 degrees. You will want to become familiar with this system and recognize then that for any angles, you can find other related angles in any of the 4 quadrants. This brings us to a rule that I would like to point out at this time. When you look in each of these different Cartesian planes for each of these different angles, you will notice that in each quadrant, there is a certain ratio that's positive every time, or as is the case in the first example, or as is the case in the first quadrant, they are all positive. We end up putting a letter A here to denote the fact that all the ratios are positive. Looking in this second diagram, the ratio that is positive in this quadrant is the sine ratio. And again, mathematically, it's because the opposite and the hypotenuse are positive, so the ratio ends up being positive. Whereas the other two involve this negative side, and so they're both negative ratios. Coming down to this example, tan is the positive ratio in this quadrant because both sides are negative that are involved. And finally, in this example, cos is positive. The adjacent over the hypotenuse gives us a positive value. That leaves us with something that's called the cast rule. C-A-S-T. And they've chosen not to start with the first quadrant simply because it makes a good acronym. So whenever we're evaluating trig ratios that are in the Cartesian plane, it's going to be common for us to write CAST on all the 4 quadrants to help us remember which ratio is positive in that quadrant. So what I'd like to do here is just summarize some components of this system. Typically, this angle here is called theta, which is the primary angle. And again, it starts at the positive x-axis. If we were to draw a line on this side of the axis, and form a triangle, this angle here is called beta, which is the related acute, and that would be related to an angle theta that's greater than 90 here. Beta is the related acute angle. This arm here is called the terminal arm because the angle ends there. And something that terminates ends at a certain location. It's also called a radial arm because it forms the radius of that circle. Something else to point out is the fact that this xy shows that these components of the triangle are actually x and y. And finally, we can label this arm, which is the radial arm, as r, which also denotes the radius of this circle. And so r squared is equal to x squared plus y squared from Pythagorean's theorem. So these are the components of this particular system that we're going to be working with. Now we're going to use this to solve some trig problems. One way that the arm can be denoted in the Cartesian plane is to give a point that shows the endpoint of the arm. So in this case, the endpoint of the arm is -5 and 4. We're going to just sketch an approximate location of this arm. So the endpoint would be -5 and 4. And that's this arm right here. The primary angle here is theta. The related acute angle would be beta. So I've drawn my sketch of angle theta. 2 says to determine the value of r. Using Pythagorean's theorem, r squared is equal to x squared plus y squared. This side based on that point is -5, and this length here is 4. R squared is equal to -5 squared plus 4 squared. R squared equals 25 plus 16. R squared equals 41. So r is the square root of 41. And remember, this is always a positive length. So we just do a positive square root. And if there was a perfect square that went into 41, we would simplify this. In this case, there is no perfect square that goes into 41. So this side here is the square root of 41. 3 now asks us to determine the primary trigonometric ratios for angle theta. The sine of theta is equal to the opposite over the hypotenuse, which is 4 over the root of 41. Now I need to rationalize that. So if I multiply the numerator by the root of 41, this is what I get. And then I will end up with 41 in the denominator. And if it helps you to write out root 41 times both the numerator and the denominator, then please do that. Otherwise, you're welcome to do this in your head at this point. The cos of theta is equal to the adjacent over the hypotenuse, which is minus 5 over the root of 41. Rationalizing, that gives us minus 5 root 41 all over 41. And finally, the tan of theta is equal to the opposite over the adjacent, so that's 4 over minus 5, which gives us minus 4/5. Finally, C says, calculate the value of theta to the nearest degree. Now remember, these ratios are all from the same triangle, so theta is the same in each of these. So it does not matter which ratio we use. I'm going to use tan theta so I can work with the minus 4 over 5 instead of a radical. The tan of theta equals minus 4 over 5. Now, similar to what you've done in grade 10, we do the inverse tan in order to find the angle. Now, what I'm not going to do at this point is write theta equals, because I don't really know what kind of an answer this is going to give me. One thing you will note now, and I'm going to at this point come back up to our 4 triangles here, is that for any ratio, there are 2 positive ones and 2 negative ones existing for any particular related acute angle. So in this case, if we look at a half here, there's also a half in this quadrant. So for 30, there are 2 ratios that are a half. There's also 2 ratios that are negative a half. So for any given ratio, there are 2 angles in a full circle that represent it. Now, if we go beyond a full circle, there's actually an infinite number of equal ratios and angles that go along with it. In the case of this question here, we don't really have to think about the other possible place that minus 4/5 would occur out of the 4 possible, because we were given a point that tells us where this terminal arm is. So we already know it's in this quadrant. So we know there's only going to be one answer for this, but what we don't know is whether the calculator is going to give us the beta answer, the related acute, or whether it's going to give us this obtuse angle. So I'm just going to write the inverse tan of minus 4 over 5. I'm not going to say whether it's beta or theta. Coming here and calculating, second function tan minus 4 divided by 5 equals minus 38.7. That's an acute angle. So now I know that the answer to this is beta. And I'm not going to write it as a negative. I'm going to simply write it as a positive, because beta is always considered simply a positive angle. It's only theta that can have a positive. And what I haven't mentioned yet is that theta can also rotate in the other direction, and so that's considered negative. That's something you will find when you take physics, that oftentimes positive and negative denote direction. And so in this case, negative is a negative rotation. So when the calculator gave us negative 38.7, it was actually trying to give us a primary angle, so it gave us the closest rotation, which was minus 38.7. What we want out of this is simply the fact that we can know what the related acute angle is for the 4 possible triangles that exist. Now in this case, we know it's this triangle. So in order to get theta, we need to take 180 degrees, which is this entire rotation from this positive x-axis to the negative x-axis, and subtract beta, and that will give us the leftover, which is theta. Theta is equal to 180 degrees minus 38.7. That gives us 141.3. This next question is to help us consider some special cases that occur. In this case, 90 degrees. And we had an example in our other lesson where 90 degrees came up, and we talked about the fact that in reality, you wouldn't have a triangle. Whenever we're on one of these axes, we end up calling the length of this arm simply 1. That comes from something called a unit circle, which you will become familiar with in grade 12. And you certainly could go look up the unit circle and you would see how it depicts all of the main special angles that exist going around this circle. So what we want to think about here is the fact that as we draw triangles, these triangles with the arm rotating, notice that the opposite is getting larger while the adjacent is getting smaller. So in effect, what's going to happen as you keep rotating this, eventually the adjacent will become 0. So what we basically have is a hypothetical triangle where both the hypotenuse and the opposite are right on top of each other, meaning there's really no triangle. They're both 1, while the adjacent is 0. Now the way I sometimes draw that is to make a triangle that doesn't really exist, but it helps to visualize what's happening. And then I label it with those values. So this is my right angle. This is 0, and these are both 1. I call it a hypothetical triangle because, of course, that's really not a triangle. It's really this 2 lines on top of each other shown on this axis. But it helps us to see the ratios. So I'm going to label the ratios here. This is the angle that we're referring to. So this is the opposite, the hypotenuse, and the adjacent. Writing out the 3 trig ratios, the sine of 90 degrees is the opposite over the hypotenuse, which is 1 over 1. And that equals 1. The cos of 90 degrees is equal to the adjacent, which is actually 0, over the hypotenuse. So we have 0 over 1 equals 0. The tan of 90 is the opposite over the adjacent, which gives us 1 over 0. And hopefully you recognize a problem here. We have division by 0. So this is undefined. So if you punch in the tan of 90 in your calculator, you will get an error because the value doesn't exist. So that's a special case. Similarly, we can do the same thing on all of these axes. So we can draw a line down here on this axis, and now what would happen is the opposite side is flat and it becomes 0, and the adjacent and hypotenuse are 1. When we come down here, the opposite is -1 while the hypotenuse is 1 and the adjacent is 0. When we come back to this location here, the opposite is now 0 and the adjacent is 1 and the hypotenuse is 1. In this question, we're given now a ratio and asked to find the angle that lies in the third quadrant. So in this case, once again, we're not being asked to concern ourselves with the fact that there's two angles that have the same ratio, 1 over root 3. We're only being asked to find the ratio in the third quadrant. So first of all, we're asked to find the values of x, y, and r. So what we need to do in the third quadrant is draw our triangle. And the opposite is 1. The hypotenuse is the root of 3, which is bigger than 1. So we're going to draw the hypotenuse a little bit bigger than the opposite. Labeling these, we have the opposite is 1, the hypotenuse is root 3. So we already have y and r. Y equals 1, r equals the root of 3. We simply have to find out what x is. X squared plus y squared is equal to r squared. X squared plus 1 squared is equal to the root of 3 squared. X squared plus 1 is equal to 3. X squared is equal to 3. Bring the 1 over and change the sign, or subtract 1 from both sides. X squared is equal to 2. That means that x is equal to positive square root of 2. Now, in this case, I do have to interpret my answer based on where it's located. So in this case, the reality is, based on my diagram, that it actually is minus the root of 2. So this x here is minus root 2. Now that I have the three values, I can go ahead and so I go ahead and do number 2 and sketch my angle theta, which goes to this terminal arm. And in 3, I'm asked to find what the value of the principal angle is, and then to find what beta is. I'm going to label beta here. Again, I have a choice of the ratios that I can use. And because I've found all the sides, I can use sine, cos, or tan. Let's use sine for this. So the sine of theta is equal to 1, which is the opposite to beta, over the root of 3. Remember, beta is our reference point. Now, once again, I don't know what the calculator will give me, beta or theta. So I will do the inverse sine of 1 over root 3 and see what value I get and interpret it from there. Second function, sine of 1 divided by the square root of 3. And that equals 35.3. So once again, That answer is beta because it's less than 90 degrees. So the calculator gave me beta. Now what I need to do is calculate theta. So theta is equal to 180 degrees subtract beta. If I take 180 degrees and go back beta, I'm back at this terminal arm. So theta is equal to 180 degrees minus minus 35.3 degrees. Putting that in my calculator, 180 minus 35.3 gives us 144.7. And that's rounded, so I'm going to put a dot over my equal sign. So therefore, we have now found the theta and the beta for this ratio. Finally, this question here doesn't tell us what quadrant the answer is in. It gives us a ratio and says determine all values of theta to the nearest degree if 0 is less than theta is less than 360 degrees, which is one full circle starting at the positive x-axis. So starting here, what angles give that ratio in this rotation? So this is where we're going to start using the cast rule. Now, this ratio is negative and it's a cos ratio. Cos is negative in this quadrant and in this quadrant because sine and tan are positive here. The only place where cos is positive is in these two quadrants, the all and the cos. So I need to draw my terminal arms in this quadrant and this quadrant. And it doesn't really matter what angle you draw it at. We really don't know what the relationship is specifically. Now you can think about the fact that this would be minus 0.785 over 1, the 1 being the hypotenuse, so the two sides are pretty close in size. As long as you have it drawn in the right quadrant, that is the main thing that you want to have happen. So we need to draw my terminal arm in this quadrant, and I wouldn't worry so much about the actual size of the triangle, just getting it in the right location. And I need, ideally, the same size triangle in the other quadrant. So I need to draw my terminal arm in this quadrant and in this quadrant, and I wouldn't worry about the size of the triangles except trying to get them about the same size. Now I won't concern myself with labeling the sizes. I don't really need that. I am going to label my theta and my beta. And keep in mind now we have two triangles. These are both beta. Now I need beta in order to get this angle and then this other rotation now that goes to this terminal arm. So there are two values for theta that I should have. So once again, I'm going to do the inverse cos. And again, I'm going to do my inverse cos of the ratio, but I'm not going to identify whether it's beta or theta. Second function, cos of negative 0.785 is equal to 141.7. That clearly is my theta because it's greater than 90. So theta is equal to 141.7. Now I need my beta in order to get this other angle that goes past 180. So now what I need to do is calculate beta. Beta is equal to 180 degrees minus 141.7, which equals 38.3. Finally, to get this last value for theta, right here, I will need to take 180 and add 38.3. So theta is also equal to 180 plus 38.3, which equals 218.3. Therefore, theta equals 141.7 degrees or 218.3 degrees. I want to encourage you, first of all, to take some time to just study those first four examples in the mind's on and become familiar with how this system works. And then look at the various examples that we have just done. And once again, make sure that you have a good understanding of the relationship between theta and beta, and also the idea that this cast rule tells us which ratios are positive, and that for any ratio that's positive, it always occurs in two quadrants, and there's always two negative ratios that occur for any given beta. So you can go ahead and practice these questions.